So in today's lab, you are going to be doing an electrophilic addition where you will do a bromination of trans stillbene. Now in this experiment, we're going to be doing a greener synthesis, and I will explain that in a little bit more detail. This is your final lab of the semester where you're actually going to be doing what we call wet chemistry. Your next lab would be to do some analysis data, so you won't have to be doing any wet chemistry. So in this experiment, you'll be utilizing concepts you've already learned. So you're not doing a distillation, but you're going to be using the microscale glassware to set up glassware very similar to doing that. You're going to do recrystallization, and you're going to be, like you normally do, measuring out and organizing your experimentation. So please make sure you come in prepared and get started immediately, because this experiment doesn't take the entire time, but can if you don't prepare appropriately. So like I said, this is the green bromination of stillbene. And in the green bromination of stillbene, you are actually going to be adding bromine in an electrophilic addition across trans stillbene. And what trans stillbene is, and you'll see an image of it in just a second, it's two phenyl rings that are on either side of a alkyl group or a vinyl group. Sorry, a alkenyl group or a vinyl group. What that means is that it's a highly conjugated molecule. So on TLC, it's going to be very apparent if you were to TLC it, because it moves around electrons. But stillbenes are important, and the reason that people look at them, stillbenes are important because they have very often biological properties, or more correctly, biochemical properties that allow them to be used in a variety of things, from antioxidants to anti-cancer agents. Now, not necessarily trans stillbene, but other kinds of stillbenes that have the same structure but may have some variations on the structure. The second thing about this experiment, so not only are we using something that's more environmentally relevant, we are going to be doing a green bromination. In this green bromination, we're not going to be adding bromine the liquid. Bromine the liquid, if not handled carefully, can be quite harmful. Now, bromine in contact with water in your skin can become hydrobromic acid, but the problem with our skin is that we can wash it all we want, but remember, we have little creases and crevices in our skin, pores and things like that, that bromine is pretty good at getting into and makes it very hard to wash away. And so while it's interacting with the water in your skin, it's forming hydrobromic acid and it starts to burn. So it's one of the few chemicals we might work with that, if not handled correctly, you're not wearing gloves, could be a little bit of a problem. Also, it produces vapors that you don't want to inhale for the very same reason. Now, it's not extremely the worst thing on the planet, but if we could do something a little bit better, why not? So we can produce bromine in a method that's called in situ. In situ means making it at the time that you need it. That's basically what it means. And so if you take any kind of bromide salt, like sodium bromide or potassium bromide, or you take hydrobromic acid, and you react it with an oxidant like hydrogen peroxide. That's why people use hydrogen peroxide in their hair, or as a mouth rinse. It's a strong oxidizing agent that can bleach your hair, can bleach your skin, bleach your teeth. Now, what we use at home is fairly dilute. It's usually about 3%. What you're going to be using is quite a bit, more than 10 times that. So it's pretty strong stuff. But as long as you're wearing your gloves, it will be perfectly fine. So you just want to make sure that you are wearing gloves and don't get it on your skin. But hydrogen peroxide, being an oxidant in the presence of something like sodium bromide, potassium bromide, hydrobromic acid, itself produces bromine. Bromine is a brownish looking liquid, and you'll see that in some of the pictures. But you'll add the hydrogen peroxide to the bromine solution, and immediately it will start producing Br2, bromine the liquid. in the flask. So you never have to measure it out, measure out the bromine directly. It's already there. Reaction. So the top one is the first of the two reactions. It's a redox reaction. You're doing a reduction, oxidation of hydrobromic acid. And so, sorry, yes, you're doing an oxidation of hydrobromic acid. And so the hydrogen peroxide will be reduced to water, which is very benign. But you're producing bromine liquid in the solution that then gets immediately used up by the stillbene, the trans stillbene, and adds in the electrophilic addition. So one thing to remember, you learned about earlier in organic chemistry, phenyl groups or aromatic rings, they don't really do these types of reactions. They don't do electrophilic addition reactions, but they can do similar types of reactions with bromine and oxidants. So that's why you want to follow the directions very carefully so that you don't get these extra side reactions that can happen. So we're going to add the hydrobromic acid. It's two equivalents, the hydrogen peroxide, and it will produce the bromine in situ as well as some water, which will mix in with the ethanol solvent. It will do an electrophilic addition, but remember when you learned about electrophilic additions, it adds across the double bond, but halogens are going to add in an anti-fashion, so we get these meso compounds. So if you were to rotate one side of your molecule, you'll see that there's a plane of symmetry, so there is no, this molecule is not chiral. So if you were to take do a polarimeter of that, you would actually get 0. And so this molecule is produced, is a solid, and you can obtain. One of your questions is, what is the name of the mechanism? We've said it a few times. Nucleophilic addition, electrophilic addition, substitution, elimination. So in the setup, you will set up a reflux. And so this image that you see here is kind of, this is actually what your reaction looks like. But what you're going to do is take your 10 ml round bottom flask, make sure it's clean and dry before you use it. Don't just assume your glassware is clean. Make sure you clean it and make sure it is dry. If there is even a little trace of water, you can use a little acetone to flush it out. You want to weigh out your trans stillbene, your E stillbene, and weigh it into your round bottom flask. So you want to put whatever you weighed out into that round bottom flask. Make sure you record your weight directly in your ELN. Please do not write anything on paper. You're going to add your ethanol, which is your solvent, right? So far we added one reagent and a solvent. And then we're going to assemble our reflux. So you have the little black parts that go on and screw on. You have your condenser, and then you'll have another cap. You're going to put your water through the bottom part of the condenser and flow out through the top. Remember, if you don't do that, then the water just flows completely out and never fills the condenser. And then you're going to put a cap with the septa, so the little black cap with the septa in it, and sit it on top. Do not screw it on, because then you're going to be creating pressure in your reaction, which you don't want. You just want it to sit on top to help prevent any little solvent that might happen to escape the condenser from coming out. So ensure that the top's not completely screwed in, but it's there. Then you're going to let this heat up in your water bath. Make sure not to crank the hot plate up too high, or you're going to shatter the glassware. So just turn it up until the water is about boiling. Let it dissolve at least most of the stillbene. Maybe a little bit is left over, but at least most of it goes into solution. Then you're going to get your syringe with the needle, and you're going to slowly add your hydrobromic acid directly through the top of your flask, of your reaction, so you don't need to disassemble anything. And then as soon as you're done adding the hydrobromic acid, remember, acids will corrode metals and it could damage the syringe, so immediately go to the sink and wash it out. Then you can, but before that, where did we say the hose needs to have the water enter through? Should it go through the bottom or should it go through the top? So once you have added hydrobromic acid, then go ahead and add your hydrogen peroxide, and you're going to do the same thing, add it slowly through the top. You're going to let it react, and eventually it should become a cloudy solution or almost clearish looking, but there should be no more color left over. Then you're going to take your flask out of the hot water carefully and let it cool down. Once it's fully cooled, you're going to neutralize it. Then you're going to filter your solid. Then you're going to recrystallize in ethyl acetate. And once you've recrystallized, you're going to filter again. So your instructions don't go through all this because they explain you already should know how to do this. But after you recrystallize, you always do a vacuum filtration. And then you're going to dry in the oven like you normally do. Just make sure the temperature is not too hot on the oven. So check the temperature on the thermometer. You're going to obtain your data like your weight, your IR data, but the NMR data will be given to you in your ELN, as well as the GC mass spec will be given to you. So you don't need to collect those. So we already have those available for you to save you some time. But you're going to do your green calculations. But one thing we want you to do is to really think about what are some of the green principles that are associated with this experiment. So go back to the beginning of your lab manual and look at what are some of the green principles. Some of them indirectly we talked about here, but what else can you think about for your procedure? So here's another pre-lab question. What is the purpose of the reflux? Is it to boil the reaction? Is it to evaporate the solvent? Is it to recirculate the solvent while you're heating the reaction? Or is it to distill the reaction? Here's another question about the NMR. So when you add your alkyl groups onto your molecule, when you add the bromines, you're making alkyl groups. So you're going to have that double bond in the middle replaced with two bromines to get rid of the double bond. So now it's basically an alkyl bromide. So why would the hydrogens on that carbon with the bromines be shifted much further down than you would normally expect alkyl bromides to be shifted? So does the bromine make the hydrogen more downfield? Does the phenyl groups make the hydrogen more downfield? Does the presence of the bromine and the phenols make the hydrogen more downfield? Does the alkyl groups not really behave like alkyl groups because of resonance? Maybe they behave differently. Or does the bromines make the hydrogens more upfield?